we are going to continue from the first video, the trigonometric equations section. Let us consider this following equation. What about we have the tangent of 3x is equal to 1 with the imposed restriction that x is strictly less than 2 pi, but it is greater than or equal to 0. Okay, let's solve for x given this constriction. So in order to solve for x, we must take the tangent inverse of both sides of this equation. Okay? Which is what we get here. Now, notice that the tangent inverse of tangent of 3x is just 3x. Okay? And so all we're left with is 3x is equal to the tangent inverse of 1. Let us now determine what the tangent inverse of 1 is. To do so, we must look at the unit circle. Alright? Then we must determine what is this asking us. Well, it's asking us at what angle does the tangent function output the number 1. Those angles, plural, are precisely at pi over 4 and at 5 pi over 4. Why is that? Well, at pi over 4, you have sine over cosine being square root of 2 over 2 divided by square root of 2 over 2. And at 5 pi over 2, you have sine over cosine being equal to negative square root of 2 over 2 divided by negative square root of 2 over 2. These both reduce to the number 1. And so it is precisely at these two angles that the tangent function will output a value of 1. So the tangent inverse of 1 is equal to 5 pi over 4 plus the period of tangent n pi, and it's equal to pi over 4 plus the period of tangent n pi. As you can see here, 3x is separately equal to this and to that. So solving for x separately, I get x is equal to 5 pi all over 12 plus n pi all over 3. And I get x is equal to pi over 12 plus n pi all over 3. Because I divide both sides by 3 here, the 3 distributes to each of these terms, and when it distributes to this, it gets multiplied times 4 to give me the 12. And when it gets distributed to this, it's just down here. Here, when it gets distributed, divided by 3, this whole thing, it goes down here and it gives me this 12, and when it gets distributed to this term, it just gives me this 3 here. Now, we must plug in values for n that remain within this interval. We won't pick negative integer values for n because that won't give us negative outputs, and we don't want that. We only want positive outputs that are strictly less than 2 pi. So let's start out with n equals 0. What does this give us? Well, notice that here this term would equal 0 and this term would equal 0. So the values that it would output will be 12 pi, or pi over 12 and 5 pi over 12. Okay? So these are two answers, and because they are strictly less than 2 pi, they are valid answers. So let's continue. What about for n is equal to 1? Alright, now here we would have pi over 12 plus pi over 3. This is going to be another answer. And let's see what it is. Well, we got to multiply top and bottom here by fancy number 1. Let's say 4 over 4. Then we get pi plus 4 pi all over 12. Then this equals 5 pi all over 12, which that is a redundant value, so we don't need to list it. We've already found it. But for the other one, when we have this guy, 5 pi over 12, added to pi over 3, now we have 5 pi plus 4 pi all over 12. This results in 9 pi all over 12. And we know 9 pi divided by 12 is just, you guessed it, 3 pi all over 4. So this is another valid answer, 3 pi over 4. Okay, and this is for n equals 1. Now let's clear up some real estate. You guys are watching this online, and so you can always rewind and look at what I erased. You can also pause me, fast forward me, take me back in time. So I don't feel bad about erasing that. Okay? So now let's do n equals 2. because we have to do this iterative process until we exceed a value of 2 pi. So for at n equals 2, we're going to have our pi over 12 plus 2 pi over 3. Okay? So then this reduces to pi plus, multiply top and bottom by 4, I get 8 pi, everything over 12. So this reduces to 9 pi all over 12. And this also, again, equals our 3 pi over 4. Which, this is a redundant value. We had a 3 pi over 4 here. So we don't care for this value. It's redundant. But when we plug it into the other equation, for n equals 2, then we're going to have 5 pi over 5 pi over 12. We're going to have 5 pi over 12 plus this 2 pi over 3. This ends up giving me 5 pi plus, I multiply top and bottom by 4, I get 8 pi over here, all over 12. So this results in 13 pi all over 12. This is a novel value, 13 pi over 12. And this value does not exceed 2 pi because 12 goes into 13 once and a little bit, not past 2 pi. Okay, so far we have pi over 12, 5 pi over 12, 3 pi over 4, and 13 pi over 12 as our non-trivial answers. Okay, you guys can always rewind and look at those, and so I'm going to clear up this real estate here. You can always rewind and look at those values. Matter of fact, I'm going to erase this whole board because getting a little... There you go. Now, n equals 3. We would have pi over 12 plus 3 pi over 3. Okay? Remember, because it was pi over 12 plus n pi, we divided both, it was pi over 4 plus n pi, divided both sides by 3, so we got pi over 12 plus 3 pi. It was n pi over 3, and now our n is 3, so the 3 pi over 3, that's where we get that. So we cancel out these 3's, and so now we're reduced with pi over 12 plus pi. This ends up becoming 13 pi over 12, and notice this is a redundant value. We've already recorded that as being one of our valid answers, so we don't pick it. So then we'll pick the other one. We have this 5 pi all over 12. We add it to 3 pi over 3. And it's the same thing as adding a pi, okay, because the 3's cancel. So I multiply top and bottom by a fancy number 1, which is 4. So 4 times 3 is 12. So this is 5 pi plus 12 pi all over 12. So this reduces to 17 pi all over 12. This is not a redundant value, so we're going to pick it. Furthermore, this value still lies within the restricted interval because 12 goes into 17 once, but not twice. It only goes into the number 24 twice. 12 only goes into the number 24 twice. And so we have not exceeded the valid answers yet. So far, I bet you're finding an interesting trend out. Every time we use pi over 12 plus n pi over 3 versus 5 pi over 12 plus n pi over 3, every time we use this equation for x, it pops out redundant values. And it actually has a lag for this guy. So every time we plug in a value here, it spits out the old value of this guy. So we can just start plugging in values for this guy to get appropriate values. Okay? So for the next one, n equals 4, we'll just plug it into this. So I'll get 5 pi all over 12 plus 4 pi all over 3. Multiply top and bottom 4, and I get 5 pi plus 16 pi all over 12. Okay, top and bottom by 4. So then this becomes 21 pi all over 12. Okay. Okay, so multiplying top and bottom here by 4, that's what got me this 12, and that's what got me that 16. We add them together and I get 21 pi over 12. Notice that this is a valid answer because, again, it still has not exceeded 2 pi. Let's do n equals 5. I get 5 pi all over 12 plus 5 pi over 3. Then multiplying top and bottom by fancy number 1, I get 5 pi plus, I got to multiply top and bottom by 4. So that's 20 pi all over 12. Now we get 25 pi all over 12, and boom. This exceeds 2 pi because 12 goes into 25 once, twice at 24, and then some more at 25. So it exceeds this interval. It's a value, this value is strictly greater than 2 pi. 25 pi divided by 12 is strictly greater than 2 pi. You can check that in your calculator, or you can think about it numerically in your head. So we stop plugging in values for n equals 5. N equals 5 is where the buck stops. So we don't plug in any more values at this point. Okay? So the only values that remain are 21 pi over 12, 17 pi over 12, and the ones that we recorded earlier. So whenever you have problems like this, what you need to do is first solve for x. And then whether you have a tangent or sine or a cosine, you have to add n times their period. Whenever you do that and you solve for x, you must do this iterative process, especially if it gives you a restricted interval. Okay? If it doesn't give you a restricted interval, then you can leave it in general, because technically an infinite amount of solutions exist. But for this restricted interval, a finite amount of solutions exist. And so we must determine all of those finite solutions.